Hi everyone, let us do a crossed Aldol condensation, product and mechanism. Another name for a crossed aldol is a mixed aldol. And it's when you have two different carbonyl compounds reacting in an aldol reaction, and I typically carry it forward to an aldol condensation. Let us show you an example of that. Now, you might think if we have two different carbonyl compounds, aren't we going to get a horrendous mixture? Where in some cases, molecule A is the enolate and attacks B. In other cases, molecule B is the enolate and attacks A. Well, let's see how we can mitigate that. Here we have benzaldehyde, and I'll give another aldehyde. Let's give acetaldehyde, okay, the one with two carbons. Let me make them the same size. With an aldol reaction, you need base and you need a protic solvent. To get the aldol condensation, where we do the dehydration, many professors use heat, but even without heat, this particular aldol reaction will become dehydrated because of the conjugation that you'll see in the product. Let me draw the product right now, actually. The first thing you got to realize is that this one, the one on the left, cannot be the enolate. Do you see why? We only have one alpha carbon, and there is no alpha hydrogen on that carbon. We do have a alpha hydrogen, three of them on this alpha carbon. So that's going to be the enolate. And it's going to attack this carbon here. So you are making connection between the alpha and the dot. Okay, let me draw you the product. Let me draw you the intermediate first. Because, again, with these reagents, typically you would stop at the aldol with the hydroxide. Okay, do you see where the alpha is? The alpha now is on the right, and we still have this hydrogen. You could draw it if you want. You don't have to. And we have this ring here. This is an intermediate. Do you see how the connection is between the alpha and the dot? Now, normally, like I said, you would stop at the aldol product. We'll label this the aldol product. But because by making the double bond here, not only do we get conjugation with this carbonyl group, we get conjugation for the ring as well. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond. That alternating pattern results in conjugation, and it's a very stabilizing effect. I have not yet put out a video on conjugation for the aldol. That will be coming up shortly. But for now, if you can make the conjugated system, you should. And so I'm going to put here, well, that's an intermediate. And so the final product is this. Dehydrate there. It doesn't matter to me if it's cis or trans. I think go ahead and go for the more stable trans if you can. Look at that. Fully conjugated. And a good way to tell conjugation is that look at all these atoms. That one, 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 and that one. They're all sp2. Okay, And then later on, forgot one, that one, all sp2. And so we'll talk about how that's a stabilizing effect when we talk about conjugation when I make that video. Okay, and so I'm going to put here as a reminder, even without heat. Okay, now there are some professors, what happens if we don't have these double bonds and we don't get this fully conjugated across a whole molecule? Then yes, many professors would put heat right here. Just a warning for my particular class, always make the conjugated system even without heat, okay? And even if without these double bonds here. Let's do the mechanism. By the way, if this is the aldol product, I would call this the aldol condensation product. And it's the final product in my mind. Okay, let's do the mechanism. Let's write it here. In a previous video, when we did a simple self-aldol condensation, the mechanism was, I believe, 5 steps. Let's see if that's the case in this reaction. Important that you draw out your alpha hydrogens. I'm going to do this a little bit faster because you all have experience now with the self-aldol. So the cross-aldol is the same thing. You're just going to attack a different molecule. So maybe I'll just be quiet. Dang it. Okay. Oh, dang it. Okay. Reassess. Because I was talking about self-aldol condensation, I drew attacking itself. Here's the deal. If you have 2 molecules that the professor gives you, they are implying that, one is an enolate, one is not, or definitely you should be using this molecule as the attack. In the lab, there are practical ways to do this, to force this enolate to attack here, rather than what I did here over here. Okay, so again, I was about to draw the product without even using this. Don't do that. Your professor gave you both molecules. You should be using both molecules. Oh, I can fix this. Oh, sneaky. Put a phenyl group there, right? That is, man, why didn't I mention I made a mistake? Okay, so now we are attacking the other molecule, the other partner, and we have this. Don't draw the H. Okay, yeah, look at that. Back on track. Never got off track. Then we protonate. Again, don't protonate with H3O+, plus, right? Don't protonate with H3O+. plus. You don't have H3O+, plus when you're under basic conditions. And the rule that I tell my students is never have an O+ plus when you're under base. Let's use water instead, and let's recreate the base OH minus. how did this turn out? Okay, there's your aldol product. We did create HO minus. But because of this phenyl group with all its double bonds, and the fact that we can do a dehydration right here to get this beautiful pattern of double bond, single bond, 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 then we're going to do the dehydration. And the way that you do the dehydration on an aldol is you reform the enolate. So we had one enolate already, you see on the screen, and the second enolate is coming up. Just grab that H, make this double bond, whoops, and then break that double bond, and we have our second time we see the enolate. We created water. Okay. And now our fifth and final step. Oh, let me write here enolate. Fifth and final step is this. And we get our final product. It's an aldehyde, so I'll draw the H. We make a double bond here, and I'll just keep it at pH phenyl. But you know what phenyl is. It's the benzene ring, fully conjugated. We did create OH minus, great. You know, that's going to be used to continue the process and go back here and get another molecule to be the enolate. We have 5 steps, I believe. 1, 2, 3, 4, 5. And if you recall, I didn't mention this last time actually. See when the leaving group leaves, that determines the RDS. Remember that from Organic Chemistry 1? And the RDS is unimolecular, right? The RDS is unimolecular, and we did an elimination. So this is E1, but it's not the typical E1 where you form a carbocation. It's an E1 where you form the conjugate base. This is the conjugate base of this. This is a special mechanism called E1CB. Okay. 5 steps is, again, even if it's crossed, just like the self-aldol. Now, I want to challenge you, and what would happen if I did this? Same benzaldehyde, but different enolate, or different molecule to be the enolate. And let me tell you one more thing. I'm going to have around 2 equivalents of the benzaldehyde. What do you think will happen there? This is the synthesis of a sunscreen ingredient, because it's going to be it's going to have so much conjugation that it absorbs UV light very, very well. And the clue is this. Do you see how I have an alpha here? And I marked it? Let me mark all the alphas, actually. Alpha, 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 alpha. But for this molecule here, we have 2 sides, alpha and alpha. It doesn't matter, again, what you take care of first, okay? Maybe you make the enolate on this side, okay? But here's the key. I have 2 equivalents, or around 2 equivalents. So I have enough benzaldehyde to add here and to add here. In the lab, for my students, we're doing a double crossed aldol condensation to make a sunscreen ingredient. Double crossed aldol, and it's going to be condensed, or you're going to run a condensation. Again, condensation in our case right now is the same as dehydration. It's an elimination of water. Okay. Those of you who are taking me for lab in the spring of 2025, draw me the product now. Understanding that I want both sides to go through a crossed aldol condensation. You will be responsible for the mechanism. Do you have to draw the mechanism for both sides? If you could get up to here, I think I'm fine, okay? Like with the mechanism. But you see the alpha on the right? I could do the same thing on the right, and I could get this condensation as well. Very, very interesting. Now look at the conjugation. Do I need to do this? Double bond, single bond, double bond, single bond, double bond, single bond, single bond, double bond, double. So ooh, single bond. Okay, issues. It's not the double bond, single bond pattern that I was used to, but. Look at this. That one, that one, that one, that one, that one. They're all sp2 still. So I have an uninterrupted system of all sp2 atoms that could share these pi electrons. So I haven't said that in the past. I'm kind of foreshadowing it on the next or in this future video. They share the pi electrons because the p orbitals overlap. Because the p orbitals, what p orbitals? The unhybridized p orbitals overlap. That's just a little bit of a tease for the conjugation video, which eventually I'll do. But right now, we all gotta get with the mechanism. Okay. I think I'll stop there. There's one more variation, two more variations. One, the intramolecular aldol, and the other one where we use LDA. Yes, I'll save the LDA discussion for later. But there, let me zoom out. There on one sheet is the cross aldol condensation, plus a little peek at what you're going to do in lab soon.